Alright, so today we're going to go over the basics of writing proofs. Before we can do that, we're going to have to talk about some properties. And these are properties that you had in algebra last year, or you should have had in algebra last year. So the first property we're going to review is the reflexive property. And I've set this up so that the left column is the name of the property, the middle column is the gobbledygook technical definition of that property, and then the right-hand column is a real-life example of that property. And so the issues that you all have with the reflexive property is confusing it with the symmetric property. Reflexive property is exactly as it says, it's a reflection. If you look in the mirror, don't you see exactly yourself? You don't see somebody that looks like you or resembles you. You see exactly what other people see, unless you're looking in a circus mirror, right? So the reflexive property, the left side, although equal to the right side, they also look exactly the same. So I put over here 3 equals 3. Or you could have x equals x. Or 2a equals 2a. The left side must look exactly like the right side. The difference between reflexive and symmetric is, in the symmetric property, the left side does not look like the right side. And with the symmetric property, because the left side is equal to the right side, we've come to the conclusion that we can flip-flop the left and the right side. So symmetric, we're flip-flopping left and right side. Reflexive, left and right side look exactly alike. So here I put, and oftentimes when you solve an equation, many of you in here, if you get 3 equals x, you convert that to x equals 3 because it bothers you. Some of you it doesn't bother you at all, but most of you it tends to. So you're using the symmetric property. Then we have the ever popular transitive property, which we talked about on Friday. And essentially the transitive property is a pattern. If, and it's a 3-step pattern, if x is equal to y, and then the next step would be that it has to start with what we ended with. So, and y is equal to something different, 3. Then put the two things that are not the same together, x and 3. X is equal to 3. You are going to get the transitive property confused with the substitution property. Because oftentimes the substitution property will look like the transitive property, but there's a fine line difference. For instance, if these are flip-flopped, if you had x equals y and 3 equals y, does that follow the proper pattern for the transitive property? Yes or no? If I had 3 equals y, what I start with, is that what I ended up with? No. So then it would not be the transitive property. In that case, it would be the substitution property, which is down below there. So note to self, if it looks like the transitive property but doesn't quite follow the pattern, that we have this middle part flip-flopped, it is the substitution property. It's a fine line difference, and one you'll argue with me on, but there it is. So then I put this one in here because we do, and we are going to start with algebraic proofs. However, we do use the addition and subtraction property in geometric proofs. If I, and you're going to see it today, if I have to take away something from both sides of an equal sign using angles or segments, that would be the subtraction property of equality. If I have to add something to both sides, that's your addition property of equality. So in this case, I gave you an example of the subtraction property of equality. Now, you wouldn't put here as a reason addition and subtraction property. You have to choose which one did you use. They both are the same. Same thing goes with multiplication, division. Since I'm dividing here, my reason for dividing would be the division property of equality. I certainly wouldn't say the multiplication property of equality. Although technically on this one, oftentimes I will go ahead and accept the multiplication property of equality. Why? Yeah, I could multiply both sides by 1/2 here and it would be the same. So oftentimes when we're doing a proof, depending upon the problem, I will accept that, only because I could see if you were thinking that way, that that's a viable reason. And then here's the substitution property. This one does not look like the transitive property. This is more of a pure substitution example. So you have a problem, x plus y equals 10. And then you're told in another step, well, x is equal to 3. So then in your third step, you replace x with 3, and you have 3 plus y equals 10. The act of replacing something with an equivalent value is substitution. So if you think to yourself, I'm replacing this with that, that's probably substitution. And then the last one on this chart, yes?
So if it follows the steps like the
Transitive property?
Yeah, the transitive property, but it replaces one, then that's the substitution. Like anytime that it involves replacing.
If for the substitution, I'll find my pen. For the substitution property to look like the transitive property, it might look like this. X plus y equals 10. If it were the transitive property, then I would have 10 is equal to 2 plus 8. What I ended with is what I started with. And then these are the same, right? So then these must be the same. So then my conclusion would be that x plus y is equal to 2 plus 8. That would be the transitive property, not substitution. However, if I switch these around and said 2 plus 8 is equal to 10, now what I ended with, I am not starting with. This is a substitution property. Fine line difference. But essentially what I'm doing is I am substituting in for 10 the value of 2 plus 8. So this is the same, right? Mm-hmm. But I'm replacing 10 now with 2 plus 8. Okay. It doesn't follow that transitive property pattern. Okay. And that's where it's a clue that oftentimes they will write it that way so that you'll say the transitive property, but it's not following the pattern exactly. Okay. There's nothing wrong with writing it that way, but it's just not the transitive property. Now, that would be the substitution.
Okay, so the transitive property would start with like 10 equals the other thing. And
right.
Then with that one, like you substituted 2 plus 8 for like x plus y or...
Exactly.
Okay.
So on the very first statement, whatever you ended with, the second statement has to start with that for it to be the transitive property.
Okay.
Okay? All right, then this last one on this particular chart here, you should be very familiar with the distributive property. So I put on here x times x plus 2 is x squared plus 2x. So then over to the right, I want you to write the following properties, which are used a lot, but they're not properties of equality. Can I take that away? Okay. So the first one we're going to look at is the commutative property of addition or multiplication. So if you'll put that off to the right. The root word in commutative is commute. Hopefully you've heard of commuters before. If you're from the East Coast, lots of people are commuters. What does a commuter do? Yes?
It's a long trip down or somewhere.
Typically a commuter is going where? From home to where? From the rural to the city probably is true. So where am I going to in the city usually if I'm a commuter to do? I'm working. So here in Arizona, if I were to be a commuter, I might commute to Tucson to work, but I definitely wouldn't want to live in Tucson, so I'd come back to Phoenix because there's no way I'm living in Tucson. Nope. Hard enough to get me to work in Tucson. But I would be a commuter if every day I went back and forth from Phoenix to Tucson and I'm physically moving, right? That's all that's happening here. Notice that I've got things that are grouped here. The same things are being grouped together. The letters or the numbers are not in the same order. So I've got A plus B plus C, and A and B are grouped. The grouping hasn't changed, but A and B have changed places. They've moved, they've commuted. Same thing here. A and B are grouped. Now they've switched places. Here I've got 2 plus 5 plus 8. If I were to add these, it makes a lot more sense to add 2 and 8 because it's easier to add in your head. So I would flip-flop 5 and 8. You do this naturally in your head anyway. You wouldn't, good heavens, you wouldn't actually write that down. So you've actually performed the commutative property in your head over and over and just didn't realize it. And so I flip-flop the 5 and the 8. Commutative property can occur without grouping. But changing the grouping is not the commutative property. Notice that all of my groupings that I had up there, the grouping never changed. The things in the grouping changed. So then what's the difference between commutative and associative? Associative property is where the grouping changes. The order of the numbers or the letters don't change, but the grouping actually changes. So notice here I've got A plus B plus C, A plus B plus C. The only difference from the left side to the right side is the grouping. Here A and B are grouped, here B and C are grouped. If I asked you to reassociate with your friends, I would be asking you to regroup, change your grouping of friends. Multiplication, same thing occurs. I've got A and B grouped here, B and C grouped here, but they're still in the same order of A, B, and C. And then I put it with numbers. The order of the numbers have not changed, but the grouping has changed. Now, could the grouping and the order change? Yes. So you could do in the same step commutative and associative property, but if you're using it in a proof, you cannot combine those two together. You'd have to separate them out. Questions on the difference between associative and commutative? All right.
Wait,
Yes.
Can you re-explain it, please?
Can I re-explain that? Okay.
No, yeah, like.
All right. So
Still looking at it.
commutative, they actually physically change places. They move from one place to another. Look at the associative. Has the A, the B, or the C changed places? Isn't A in the first slot, B in the second slot, C in the third slot? They
Yeah.
haven't changed places, right? The only thing that's different from the left side to the right side is that now A and B are grouped here, but on the right side, B and C are grouped. So it's changed from here to here is grouping. When grouping changes, that's your associative property, and in this case of addition, because it's an addition problem.
Okay.
Whereas above, notice that the grouping here did not change. I still have A and B grouped together, but A and B have physically changed places. A is in the first slot, now A is in the second slot.
Okay.
C hasn't changed. It could have, but it didn't. Does that make sense? Okay. So then the last part down here talks about the symmetric, the transitive, and the reflexive property in relation to segments and angles. And you had a flashcard that has said that angles are, the addition of angles are reflexive, symmetric, and transitive, and same thing with segments. And so here are just some examples of what that might look like in a proof. So in a proof, you might see a statement that says the measure from P to Q is equal to the measure from P to Q. Remember, the reflexive property, the left side looks exactly like the right side. Same thing with angles. The measure of angle 1 is equal to the measure of angle 1. And oftentimes we use this reflexive property, and you'll see it today, to hit you upside the head and say, remember, this value is equal to itself, and then we're going to take that and we're going to substitute it in for something else. Or we're going to take it away from both sides, or we're going to add it on to both sides. Then the symmetric property, you're just flip-flopping the left and the right side of the equal sign. So if you've got AB is equal to CD, then the next statement would flip them around. CD is equal to AB. Notice that the left and the right side don't look alike. They're just flip-flopping. Same thing with angles. And the last part, transitive, look for that pattern. Transitive comes in 3 parts. If this and this, then that. So what you end up with in the first part is what you start with in the second part. And then the third part is the combination of the two that weren't alike. So it follows that pattern. So when you're done, I want you to flip this over onto the other side. That is what a proof should look like. Anybody against me taking this away? Okay. In your homework, you're going to be given either full proofs with the statements and reasons mixed up, or you're going to be given all the statements and you have to come up with the reasons. I want the entire full proof written in your homework, not just a list of statements. Or I'm sorry, just a list of reasons. So you do have to write everything in there. If all I see are your reasons, I won't accept that as a question done. Done yet? No? Yeah. Okay. So then if you flip this over, you should see this on the back, correct? This is the pattern that your proofs will take in this class. You'll always see me doing 2-column proofs. If I give you a paragraph proof, do it as a 2-column proof. All right, so the very first thing that we're going to do is an algebraic one. Every proof you're going to be given something. And then you're going to be told what you have to prove. So for our first proof, we're going to do an algebraic one, because you're familiar with how to do the algebra, so you ought to be able to come up with the statements. The proof is going to be your solution in this case. So x is equal to negative 13 over 4. Typically you will have a picture, but because it's an algebraic proof, there's not a picture that goes with it. All geometry proofs should have a picture. If there's not a picture, then you draw one of what they're describing in the given. You must draw one yourself. Then you have this area here where you should pre-plan your proof, and we'll talk about what to do with that here shortly. Your 2 columns, you do have to head your columns with statements and reasons. And you do have to have a T-chart in here. Your reasons will always come from the following: definitions, postulates, theorems, corollaries, and properties. Corollaries only has 1 O. Corollaries. 2 L's and 1 R. Alright, so here's what our proof planning is going to look like. So whenever you're given this given, and you got this proof, you have to ask yourself, how am I going to go from here to here? So algebraically, here's our plan. What would we do first? Algebraically. What's the first step that I could do? Yeah, not 3. We could subtract 3 halves from both sides. We could, right? I want to get more statements in here, and plus I don't like to work with fractions. So if I don't like to work with fractions, what might I do? Yeah, I want to get rid of that denominator. So how do I get rid of it? Yeah, multiply this whole side by 2 and this whole side by 2, right? What property would that be, multiplying both sides by 2? Actually, multiplying both sides by 2 would be the multiplication property of equality. The act of distributing it in on the left side, that's your distributive property. So to go to here, negative 4x plus the 2's cancel, 3 equals 16, that would be your distributive property. So here we would have multiplication prop of equality. Here we would have the distributive prop, and I'm just kind of pre-planning it out here. I'm just thinking to myself. Then what would you do? Then you would subtract 3. What property would that be? Subtracting 3 would be? Subtraction property. Do not abbreviate subtraction property though, because it looks like substitution, right? And then finally, what would you do? Divide both sides by negative 4. And what property would that be? dividing both sides.
Multiplication and division.
But you have to use one of them. You can't use both. So
Oh.
because I'm dividing, it would be division prop of equality.
I thought that's was just the name of it.
You have to separate it. No. Yeah, because instead of writing it 4 different times, we put the addition, subtraction together and the multiplication, division together. So we kind of have a plan, don't we? So here's what our plan's going to look like. We're not going to show all this subtracting 3 and dividing by 4 on both sides. We're not going to show that part. The only part that we would actually show is this part, because that has to come before we distribute. So your very, very first statement, 100% of the time, is always your given. Where do you start? Start from the starting point, you're given. So you've got negative 2x plus 3/2 is equal to 8. If I left that blank in a proof, every one of you should get that right if you're paying attention. The very first statement's always your given. Where'd I get that from? Where'd I get it? The given. So 100% of the time, your very first reason is given. So you should know that one also. Whether you know anything else about a proof, those are the easy parts. Then you have to start doing stuff. So the first thing we did in our plan was, okay, we decided instead of subtracting 3/2 from both sides, we're going to multiply both sides by 2. So in our second step, and you do have to number or letter your statements and reasons, we are going to multiply this side by 2, and we are going to multiply this side by 2. Didn't we say above that that was the multiplication property of equality? So my reason for multiplying both sides is multiplication prop of, and you can use an equal sign for equality. Now here's where we're not going to show our distribution arrows. I mean, you might have shown them up here. We're not going to show that in our proof. We're just going to show the result. The result of multiplying by 2 was negative 4x plus 3 was 16. We go from here to here. I actually did what? How'd I go from here to here? I distributed. So my reason for 3 is the distributive prop of equality. And then according to our plan, we're going to subtract 3 from both sides. We're not going to actually show the subtracting of 3. We're just going to show the result. Wasn't the result up here negative 4x is equal to 13? And your reason is always, if you get stuck on your reason, go to the step above. What did I do here to get to here? I subtracted 3 from both sides, right? That is your subtraction property of equality. And then the next step was to divide both sides by negative 4. The result is actually our proof statement, isn't it? To go from here to here, we finally got to our proof statement, which was above. That means we're done, but we have to come up with our final reason. What did we do from here to here? Divided. So that is our division property of equality. Tonight's homework is going to be difficult for nearly all of you. It is not supposed to be easy. We're not done. We have one more proof. Oh. So now we're going to do a basic geometry proof. I want you to write everything down, and then we'll talk about the steps. Can I take this away? Hurry, hurry. You guys have to write a lot faster. Yes, so this one you're going to need to do on graph paper. Your own graph paper. So you're going to set it up in the same 2-column format. So this might be a type of problem that you're given in your textbook. It might look just like this. I need you to write down everything you see up here. The given, the proof, the picture, the statements, and then the reasons are left open. Write as fast as possible. this is typically where I tend to get just the list of reasons. And that's what I don't want to see. I want to see the whole proof. Now, if you get stuck, the answers are on my website. Do you think it's going to do you any good to just copy the proofs? Yes or no? No. But I don't mind you going there to looking to see what they are, but you need to study. Why is this the reason for this stuff? And if you don't know why, you need to circle it, highlight it, so you can ask that question. Why is it this and not that? Well, we're going to put a plan in there, so you need to have space for it. Typically, you'll see me working my proof backwards. But in this case, it doesn't work that way. Yes, absolutely, everything. Connor, you sick again?
Yeah.
And you will not have to do full proofs on your first test at all. It might be a full proof where the statements and reasons are mixed up and you have to unscramble them. Or it might look like this, where you have the statements and you have to come up with the reasons. Or there could be some statements and some reasons, and so you have to fill in the blanks. About ready? All right, I want you to look at the given and what I did to the picture. You always want to take the given and apply it to your picture. So since they said that the measure of angle VZX is equal to the measure of angle WZY, what did I do? What did I put here? Arcs. I'm trying to tell my eyeballs that these two angles together, angle 1 and angle 2, make up VZX. And they are exactly equal to these two angles, angle 2 and 3, that make up WZY. So the picture is showing us that this angle here, and this is part of my pre-plan, this angle here, measure of angle VZX, is made up of two angle measurements, aren't they? VZX, what angles make up VZX? Name them with these. Angle 1 and angle 2. So, what property tells me that I can take two smaller angles and say that they add up to the bigger angle? What addition? Close. Who said that? Say it loudly. Isn't this the angle addition postulate? Two smaller angles add up to a bigger angle? If we were talking about segments, it would be the segment addition postulate. anytime two smaller pieces add up to the bigger piece, so I'm going to put over here to the side, angle, addition, postulate. Because I'm pre-planning. I'm going to probably use this in my proof somewhere. And same thing for this one. The measure of angle WZY is equal to what two angles? 2 and 3. So angle 2 plus angle 3. So that's also the angle addition postulate for both of those together. Since they have the same reason behind them, I can probably put them in the same statement. And you see that down here, don't you? They wrote theirs backwards from mine. It really doesn't matter. And then, what do you notice about this side and this side? Yeah, they both have angle 2 in there, right? Angle 2 is part of their sum for both of them. Couldn't I replace VZX with this value? If I replace, what am I doing? I'm substituting. And I'm going to replace WZY with that value. That's our substitution property of equality. All I did was take this original given and I substituted it for these values that we determined by our brick of knowledge, that stack of flashcards you're studying. Where did I come up with that? And that's where this is starting to come into play that you had asked about earlier. There's your addition postulate, angle addition postulate coming into play. Now, can I use some algebra here? Notice that I want to come from here to here, and we'll talk about using M versus not using M. It's a style. How can I make this look like that? They both have an angle 2 in common. Can't I subtract it off? So won't I end up with angle 1 is equal to angle 3 if I use the subtraction prop of equality? So I've kind of planned out what I'm going to do. Look at what they did. Where'd they come up with this? 100% of the time, isn't your first reason a given? So reason number 1, given. Where did this come from? Two smaller angles adding up to the bigger angle. Yeah, so these two really don't have anything to do with each other yet. They are separate from each other. But we did use our knowledge that, oh, looking at the picture, I see that the two smaller angles add up to the bigger angles, so we're going to use that reason as the angle addition postulate. That was one of the postulates that had a name. If it didn't have a name, I'd make you write out the whole postulate. And then we have this one. Where did they come up with this? You have to now start to go above. If you don't know quite what to say for reason number 3, look above. How did we go from here to here to here? Yeah, we took this and it became angle 1 and angle 2. Where did they get that? They said, oh, this is equal to this, so we replaced it. We substituted in here. Then this side got replaced with this. Because it's replacement, it is substitution. Substitution property of equality. Then we get to statement 4. The measure of angle 2 is equal to the measure of angle 2. What property does that look like? And we didn't put that in our pre-planning. And here's why they're doing it. They're hitting you over the head. They're saying, remember, angle 2 is equal to itself. Because aren't we getting ready to take angle 2 out here to get to our proof statements? If I take the same amount off of each side, isn't that the subtraction property of equality? Because I maintain my equality. So this is the reflexive, and yes, you do need to have it in there, property of equality. You're being given the statement so that you learn how to form a proof. And then finally, to go from here to here, we took away this off of both sides, and we ended up with a measure of angle 1 equals a measure of angle 3. What property is that? Subtraction property of equality.